Well, hello, hello. Welcome to the exam 4 review. And let's get going so we don't spend too much time on this. Okay. Again, we're reviewing content out of chapter 4. We talked about inverse functions, we talked about exponential functions, logarithmic functions, and then we did some systems in chapter 5, and then we ended up with solving systems by using matrices. Okay, so let's go ahead and get started here. It says for the first example, for each function graph below, state whether it is one-to-one. So if it is one-to-one, it needs to pass that horizontal line test. Okay, well, let's see. I think, let's see if I could do a good horizontal line here. That will be a good pass, good pass, good pass, good pass, good pass, good pass. Yes, this is a function and it is one-to-one. We can also perform the horizontal line test on example 2 and it will pass. I just want to be careful here. Yes, 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 yes. So graph 3 will also pass the horizontal line test. Example 4, that's a fail. Because when we perform the horizontal line test, the horizontal line intersects the graph more than once, so it fails. Same thing with example 5. Again, when we perform the horizontal line test, it intersects the graph more than once. And for example 6, bam, right here, bam, or right here, or right over here, okay? And I understand it, like right here, it will be okay. But any one of these sections, it fails the horizontal line test. So therefore, it is not one-to-one. Okay, so turns out that all of these examples were no. Okay, moving on to example 2. For each pair of functions f and g below, find f of g of x and g of f of x. Okay, let's look at some definitions first. F of g of x. What's happening here is that here we have an entire function g. Okay, here's an entire function g. And what that's going to be is going to be placed into f. So notice how f is 2 divided by x, but x is now going to get replaced by 2 over x. So let's simplify this. If you forgot, this is a fraction. So we have 2 over 1 divided by 2 over x. We keep the first fraction the way it is, change to a multiplication, and we flip the second fraction. We see that f of g of x is just x. Okay, that's a good direction, or that's going in the good direction of saying that f and g are inverses. We need to check what happens when we take f and we drop it onto g. So let's see what that looks like. G of x is 2 divided by x, but f will be in place of x. Oh, this is the same thing, so it's just going to be x. Therefore, because both of these solutions or simplifications are just x, then f and g will be inverses. Let's look at the second example here. We have, again, we're trying to do f of g of x. All of this is going to be replacing that variable x. So that is, let me write that here. I guess I could just, no, I'll write it here. Again, so instead we have that negative out front, and then we write what g is, x minus 6 minus 6. Let's go ahead and simplify this. We're using a little bit of distribution there, so negative x plus 6 minus 6. We notice that the 6's cancel out, but the final answer is negative x. That is not going in the direction of these two functions being inverses. If anything, I could probably already say that they are not, but of course I got to give an answer here. So what happens when f is dropped into g? Well, here is g. Let me use an eraser real quick. Well, here is g, but all of this will take place instead of that x. So that will be negative x minus 6 minus 6, and this turns out to be negative x minus 12. So again, we had already had a pretty good feeling that this was not going to work out based on this result. This even confirms it even more. These two functions cannot be inverses. In example 3, we have two functions, the function g and the function h, and they want us to do a few things in here. Okay, what does this notation mean? That is the inverse. That is the inverse of g of x. Well, how do we do that? Well, to do that, let's do this. We have g of x is equal to x plus 9 over 7. Replace g of x with the common y. And then, so here we are replacing g of x with y. Right now, what I'm about to do is I'm about to solve. Oh, I'm sorry. My apologies. I'm going too fast. Erase. We need to swap x with y. So that this y becomes an x. This x becomes a y. And now my goal right now will be to solve for y. To do that, it seems like I need to multiply by 7. So we get 7x is equal to y plus 9. To get y by itself, I'm removing 9. So I'm going to write it like y equals 7x minus 9. Okay? And so here, the inverse of g of x is 7x minus 9. What does this notation say? G of g inverse of 1. Okay? What that looks like is g, the inverse of g of 1. And what is that equal to? So what they're asking us to do here is, here's the inverse function for g. And instead of using x, they want us to go ahead and use 1. Let's see what that is. Again, they want us to use the inverse. Okay, so that 7 times 1 minus 9. That's equal to 7 minus 9. That's equal to negative 2. So then, that is g of negative 2. G is this. So we have, well, maybe I could do it up here. Negative 2 plus 9 divided by 7. That will be 7 divided by 7, which is equal to 1. So in that particular example, it seems like I needed to use the definition of function composition. Interesting enough, that here they had the inverse. Okay, I guess I could have easily said that that's just equal to 1, but I think it's probably best just to plug it in. I guess it gives you a little bit more practice. Okay, alrighty then. So let's look at this example here with h, the inverse of h at 0. And so how do we find the inverse? Well, to find the inverse, we're going to swap every x with y. So in any case, we're just swapping the order. So we have 8 comma negative 1, 5 comma 0, 6 comma 1. We also have 0 comma 4. We have negative 2 5. But they want us to know what happens when the input is 0 on the inverse. What is the output? And the output happens to be 4. What is the output of the inverse when the input is equal to 0? The output will be equal to 4. Okay. All right, let's move on out of that. We got 25 questions. The one-to-one function g is given below. They want us to find the inverse and also state the domain and range of the inverse. Okay, let's go ahead and get started here. I can move this chair a little bit lower. All righty then, let's go ahead and get to business. All right, so here we have g of x is equal to negative 2x plus 1 divided by 8 plus 9x. To find the domain of this function, we know that whenever we have a fraction, we cannot divide by 0. So in order to find the domain, let's find the value of x that makes the denominator equal to 0. And that value is negative 8 over 9. So therefore, we can choose any value for x. We can choose any value for x, except 8 over 9. And the way I'm writing it is the way we will skip 8 over 9 using interval notation, okay? So that you have a graphic representation of what I'm talking about. This is the number line. This is the number here, negative 8 over 9. So basically we're saying you can choose any number greater and you can choose any number less than, but you cannot choose the number negative 8 over 9, okay? All right, for the range is a little bit more, it's a little bit more interesting because we need to remember or recall asymptotes of rational functions. So when we have g of x, and I'm going to write it like so, okay? Negative 2x plus 1 over 9x plus 8, we were looking at the degree or the exponent on the variable x's. Since they have the same degree, then the horizontal asymptote for this rational function will be, the horizontal asymptote will be y equals negative 2 over 9. So therefore, if you think about what's happening here with this graph, kind of give ourselves an idea, negative 2 over 9, let's say somewhere here, okay? We're going to have some branches. We can choose any value of y, or the output will be any value of y except this horizontal asymptote. So therefore, the range of g will be, let me just write it like so, negative infinity, comma, negative 2 over 9, union, negative 2 over 9, positive infinity. Okay, we've done a whole lot of work and we haven't really answered what's going on here. Let's go ahead and get to it, because I think we got, even though I don't know what this inverse function looks like, I already know that since this is the domain of the function, then this will become, let me use a different color, this one, then this will become the range in the inverse. Since this is the range of the function, this will be the domain of the inverse. Okay, so I already know that, even though I do not know what the inverse of g will be. Well, let's find that. Y is equal to negative 2x plus 1 divided by 8 plus 9x. Swap x and y, so that will become an x. And this x will become now a y. So will the x in the denominator, it will become a y. It will take a couple of few steps, but let me just remind you that here we're going to multiply by 8 plus 9y on both sides. These quantities will cancel each other out, but here I am going to distribute. That would be, let's see if I got a little bit more room down here. Yes, I do. That will be 8x plus 9xy. It's equal to negative 2y plus 1. My goal will be to get everything that has a y on the same side and everything that does not have a y on the other side. So I am going to move this quantity over to this side. Actually, I think I'm gonna take that back. I'm gonna move this quantity to this side, okay? At the same time, I'm going to move this quantity over to that side. Check it out. This quantity becomes positive because it is negative on the other side. This quantity that is positive will become negative. And then we notice that we can factor out a y, 2 plus 9x. Oh, let me continue writing this out. But let me move to this space right here. This is what we have. Y times 2 plus 9x is equal to negative 8x plus 1. We're going to divide by this quantity here so that y is by itself. So we have that y is equal to negative 8x plus 1 over 2 plus 9x. Okay. So what's going on here now? Well, let's see. Well, this will be the inverse. The inverse will be this. Okay. Notice that the domain of the inverse will be, well, you cannot have a denominator equal to 0. So let's find out what that is. And divide by 9, we get x is equal to negative 2 over 9, which is what we already knew. And notice that in this case, the horizontal asymptote will be negative 8 over 9. So the horizontal asymptote will be negative 8 y equals, which agrees with what we had over here. Okay. So all of this makes sense. Oh, it was a very long example, I will admit that. But hopefully, with practice, you guys will be successful. Just give yourself some practice. Give yourself some practice. All right, let's see. All righty, then let's move on with this. Number 5, we got some exponential functions here, okay? And they want us to translate it, okay? And so basically, what this does, it moves the graph left 2 units. What this does, it moves up the graph 4 units. And so let's see, so left 2, 1, 2, up 4, 1, 2, 3, 4. And so therefore, here's the horizontal asymptote. And so the graph will look something like this. All righty then. You guys know how to do that, so I have no words about that. You guys are comfortable with doing something like that. Here they want us to graph the exponential function. So a few things. What is the horizontal asymptote for an exponential function? So I said that was y equals 0 unless it is being moved up or moved down. In this case, nothing is being moved up, nothing is being moved down. So therefore, the horizontal asymptote will be y equals 0. Because the base, well, you know what? Because the base is well, here's what I'll do. You know, I don't want to just let's just choose two values, x equals 0. Okay, x equals 0. So if x equals to 0 and we plug it in, that will be 1/2 0 plus 2, which is 1/2 to the power of 2, which is 1/4. Again, ladies and gents, you can type the ordered pair 0, 1/4. 0, 1/4. We can actually plug this in. 0, 1/4, so somewhere around here. We need a second point. I'm going to say let's choose -2. Just choose -2. 1/2 -2 plus 2. That is 1/2 to the power of 0. Any base other than 0 raised to the 0 power must be 1. So we have the ordered pair -2, 1. And again, this is all we need to let Alex do its work. The domain of any exponential function will be all real numbers. And in this case, the range will be all the values that are greater than 0, all the y values greater than 0. Again, from here up. From here up. Okay. Alrighty then, let's move on. We don't want this to be too long, just enough. 7. Tommy deposited $4,000 into an account with 2% interest, compounded annually. Okay, so this is compound interest formula. So the future value is equal to the initial investment, 1 plus the interest rate divided by the number of times the interest is compounded in a year, raised to the power of NT. So just to get some information here, assuming that there are no withdrawals, how much would it be saved after 10 years? So T is equal to 10. Initial investment is 4,000. Interest rate is 2%. Decimal representation 0.02. And we're good to go. Oh, and N is 1 because it is compounded annually. So therefore, N will be equal to 1. Here I go. That will be 4,000. 1 plus, and I'm just going to write out everything. 0.02 divided by 1. 1 times 10. And you probably say that was kind of silly, but yes, but what if the next example, N is equal to 2? You know, so I wanted to write everything out. That will be 4,000. If I do this inside the parentheses, that is 1 plus 0.02 raised to the power of 10. 4,000, 1.02 raised to the power of 10. Let me use my handy calculator and let me tell you what the answer is. 4,000 raised to times 1.02 raised to the power of 10. Please be careful with your parentheses. And since 2 decimal places because it's money, so 4,875 with 98 cents. Rounded to the nearest cent. Bam, there it is. Alrighty then. Moving on. Rewrite as an exponential equation. Okay, before I do this, let's go ahead and review a little bit. Okay, before I do this, let's review a tiny bit. We have a base that is raised to an exponent and is equal to an answer. That is equivalent to the logarithm of that base, okay? Argument equals exponents, okay? So basically they have the same pieces of information, a base, an exponent, and of course the argument in this case will be the answer. So to write this as an exponential equation, Here's the base 7. Here's the base 7 raised to the exponent negative 1. That's equal to 1 over 7. Here they want, oh, so they want us to put the answer here. Okay, fine. Here they want us to use a logarithm with a base of 2, argument 32, exponent 5. So 2, 32, 5. How do I read this? 2 raised to the 5th power is equal to 32. Alrighty then, moving on. That was actually not bad. Here we got a little bit of transformations. We want to move this to the left 1 unit and up 3 units. Okay, left. So if you move this to the left, remember that in a logarithmic function, we have a vertical asymptote. So if you move this to the left 1 unit, then this vertical asymptote is also going to move 1 unit. Let me erase the original one. And then what else did we do? We went up 3. So left 1, up 3. So basically we got something that looks like this. Not bad at all. Not bad at all. Not bad at all. Let's keep going. I had a feeling that they were going to want us to graph it. Okay. So good old table technique. Can't go wrong with this. Okay. Again, the logarithmic function has a vertical asymptote of x equals 0 unless you move it to the left or you move it to the right. Here we are not moving it to the left and we're not moving it to the right, so this will be our vertical asymptote. Okay, so let's see. We're going to choose x values greater than 0. So let's begin with x equals 1. Okay, we have the logarithm base for 1. What does that mean? What is the exponent on 4? What is the exponent on 4 so that the answer is equal to 1? The exponent on 4 must be 0 so that the answer is 1. So we have 1 comma 0. 1 comma, oh, I forgot the negative, but in this case, doesn't affect it. 1 comma 0. Let's choose, let's say, for example, 4. Negative, the logarithm base for 4. Okay, so we got to follow the order of operation. Let's do first this. 4 raised to what? So we have a negative. Just don't forget about that negative. 4 raised to what power is equal to 4? 4 raised to what power? Let me get rid of that negative first, and then I'll put it at the end. Okay. 4 raised to what power will be 4? That will be 1. And you put that negative, you get negative 1. So we get 4 comma negative 1. 4 comma negative 1. And that's all we need, because we can use the Alex tool to connect those 2 points with that particular curve. The domain will be all values of x greater than 0. The range will be all real numbers. Okay, that wasn't that bad, and we kind of halfway through the review. It says rewrite as requested. Well, in this particular case, do not forget that if you have the natural logarithm, the base is e. So here's the base. E to the power of y is equal to 4. Here, as a logarithm, they want us to say, okay, they want us to say the logarithm base e is equal to 5 equals to x. Okay, logarithm base E5 equals x. Base, okay, base, the exponent on the other side equals the argument. I think I want to say ln of 5 equals x because ln of the logarithm of base e can be simplified with ln. Okay, so I don't know exactly how Alex wants you to write that down. Okay. All right, number 12, use properties of logarithms to expand. Okay, let's do a little bit of expanding here. Let's review a property though. Let's review a couple of properties. The logarithm base b xy is the logarithm base bx plus the logarithm base by. The logarithm base bx raised to the power of r is r logarithm base bx. So let's see how we can expand this. I clearly see a multiplication in the argument, so we can write that as the logarithm z plus the logarithm x squared. And then this we can rewrite as the logarithm base 10z plus 2 times the logarithm base 10x. Notice that I'm saying base 10 because if we don't see a base, it's because the base must be 10. Okay. All righty then. All right. Okay. We got number 13. Let's see what number 13 is all about. 1 second here. All righty then. Let's see. Okay. Let me write one more here just in case we missed it. The logarithm base b x over y is equal to the logarithm b x minus the logarithm base b y. So basically a division in the argument turns out to be a difference. All right, so what can we do here? I think the first thing I notice is here is, oh, we got these things on the outside, these coefficients in front of these logarithms, and these coefficients will become exponents. So we have the logarithm base c w to the 5th power minus the logarithm base c x to the 1/4 power plus the logarithm base c y to the 4th power. Okay. Now we see here a difference, and that difference, okay, let me, before I do that, let me write it like so. The logarithm base c w to the 5th power minus the logarithm base c, that will be the 4th root of x plus the logarithm base c y to the 4th power. So now I'm going to say this difference becomes the logarithm base c w to the 5th power over the 4th root of x plus the logarithm base c y to the 4th power. And then this sum becomes a multiplication. So like so. Final answer, the logarithm base c w to the 5th power divided by the 4th root of x times y to the 4th power, like so. Questions? No questions? Moving on. Evaluate the expression. So basically, 6 to what power will give us 1 over 6? That will be -1. Remember, it's those negative exponents that turn the base into a fraction, okay? That was kind of a little thing that we said in class that can help us remember what do negative exponents tend to do. Oh, what about this one? I don't see a base. Well, that means that the base is 10. 10 to what power equals 100? Of course, that will be 10 squared is equal to 100, okay? So again, you could probably do these examples like so. 6 to what power is 1 over 6, and 10 to what power is equal to 100. Maybe that can help you out in answering some of these questions. Use the change base formula to compute the following logarithm. Round your answers to the nearest thousands. Okay, we said that the logarithm base bx is equal to, if we want to use the change of base, okay, we could say that the logarithm base a, I think I'm going to use base a, x divided by the logarithm base a, in this case will be b. But what I recommend there is use the common base 10. So basically, this change of base formula becomes the logarithm base 10x, the logarithm base 10b. So in the case that we have here, okay, we can rewrite this as the logarithm base 10 4 divided by the logarithm base 10 1 over 3. And then I can use the calculator to evaluate this and round it to the nearest 3 decimal places. So I'm going to use my handy calculator now. I got logarithm base 4 divided by, make sure you follow your parentheses correctly, the logarithm 1 divided by 3. Make sure that, again, you're using your your calculator correctly, and we get negative 1.262. Okay, 262. Moving on to the next example, it seems like we're now solving some sort of logarithmic equations. And okay, all right, got a little bit of everything here. Let's get busy. I mentioned in class that sometimes when we're solving logarithmic equations, we prefer to solve an exponential equation instead. Why do I say that? We can rewrite this as 3 to the power of 4 is equal to 4x minus 19. This will be equal to 81. 4x minus 19. We add 19 to both sides, and we get 100 is equal to 4 times x. Divide by 4, divide by 4. 25 is equal to x. So check the answer to make sure that the argument is not negative, and in this case, 25 does not make the argument negative, so we are going to accept this solution. Okay. Notice the strategy. The strategy was to rewrite this as this will be the exponent. I'm sorry, this will be the base. That will be the exponent, and this is the answer. Okay. And using a rewrite, we were able to solve this a little bit easier. Okay, what do we got here? It seems like we got logarithms on both sides of the equation. I am not so much fan of that. Why don't we go ahead and put those logarithms on the same side? Okay, so let me see. We're going to have negative logarithm base 5 x minus 3 plus the logarithm base 5 x plus 1 is equal to 1. And even then, I don't like the way this is written, so let me rewrite it like so. Look, check this out. The logarithm base 5 x plus 1 minus the logarithm base 5 x minus 3 is equal to 1. I took a shower and my hair is still all wet, so I should have given it a chance to dry out. So then what do we got here? We got a difference, and we can rewrite this as logarithm base 5 x minus 3 over x plus 1 is equal to 1. And you're probably saying, well, what good is that? Think about what we did in the previous example. We rewrote it as 5 to the power of 1 is equal to whatever the argument is. We rewrote it. 5 to the power of 1 is just 5. We got to get going here. So we need to get rid of this fraction by multiplying by x plus 1 on both sides. Here we get x minus 3. But here we get 5x plus 5. I'm just going through the motions now. I'm going ahead and, bring the x's to the same side. Move the constants to the other side. Okay, so these cancel. 5x minus x is 4x is equal to negative 8. Dividing by 4, x is equal to negative 2. I want to be really careful to see what happens. And, oh no! Look at that. Negative 2 plus 1, that's negative 1. Even here, negative 2 minus 3, that's negative 5. That negative 2 makes the argument or arguments negative. So therefore, we got to reject this solution. And therefore, this has no solution. There's nothing to say about that example, just that it doesn't have any solutions. Okay, all that work for nothing, pretty much. It is what it is. Number 18. Solving an exponential equation with, I think, common bases. 64 is the same thing as 2 to the 6th power, while 32 is 2 to the 5th power. Since these bases are the same, we can just cancel the bases and we're left with solving the following equation, okay? 6 is equal to 5 times negative x minus 4. Okay, so let me go ahead and do that. We get negative 5x, we get negative 20, and I'm just now going through the motions. Okay, going through the motions as I would any other time. Okay. All right, so let's see, dividing by negative 5, dividing by negative 5. So we get negative 26 over 5 is equal to x. And this is okay. There are no problems with solutions to an exponential equation. It's the logarithms that you got to triple check. Okay, so this is good to go. That was actually not that bad. Let's see what kind of mess we can get ourselves into in the next example, because 3 squared is not equal to 6. So we won't be able to do that. Instead, the only thing that we can do here is to take the logarithm out of both sides. So I'm going to take the common logarithm out of both sides. Let me rewrite this. Okay, because I couldn't get a common base. We just won't be able to, okay? So what we do is we say, take the logarithm, and I'm going to take the common log out of both sides, and then kind of rely on the logarithm properties, because this exponent now becomes a coefficient. And then we see that this is nothing but a multiplication, so we're going to divide by, that was kind of silly. We're going to divide by this quantity, negative 2 times logarithm 6. So we get that, let me do that here too. That y is equal to the logarithm base 10, 3 divided by 2 times the logarithm base 10, 6. What does it say? Round your answers to the nearest hundredth. So that is 2 decimal places. So time for the calculator. Again, here's where you want to be careful with your parentheses. If you're not careful, it's very likely that we'll make a mistake. Okay, so I'm now typing in logarithm base 3, logarithm base 10, 3, negative divided by negative 2, logarithm 6, and 2 decimal places, we get negative 0.31. End of that story. Let's move on. Number 20. Oh, we got a application problem. Okay. The number of milligrams, D of H, of a certain drug that is a patient's bloodstream 8 hours after the drug is injected is given by the following function. When the number of milligrams reaches 3 milligrams, so when this number is equal to 3, the drug is injected again. How much time is needed between the injections? Round your answers to the nearest tenth or 1 decimal. All righty then, let's see what happens. So they're telling us that they want us to find the time in hours in between injections. Okay, so here we go. I think this part of the sentence was key. When the number of milligrams reaches 3, so we're solving 3 is equal to 20 Euler's number raised to the 0.05 h. Well, can't really do anything yet, but let's take away this 20 out of each side by dividing by 20. So we get 3 over 20 is equal to E raised to the power of 0.05 h. Can't really do anything with that h because we need to bring that down. So right now I'm going to take the natural log out of both sides. This will be inside of a parentheses. I'm going to take the natural log. So when I do that, the exponent comes down. Okay. However, the natural log of E is equal to 1. So that basically goes away. And so therefore, to get h by itself, we do a division. So we have the natural log of 3 over 20 divided by negative 0.5. And it's time for the calculator one more time. This time we're using the natural log. Okay, so make sure you click that correctly. No, natural log of here, use parentheses, 3 divided by 20. Then divide by negative 0.5. And I get 3.8 hours. Okay, so that's rounded to 1 decimal place. Number 21, how much should be invested at a rate of 5.5% per year, compounded continuously? Okay, that's a key word right there. A is equal to the principal times E raised to the power of R times T. So how much should be invested now? How much should be invested now? This is what we're looking for. When the following interest rate compounded continuously to have 2,000 in 4 years. Oh, to have 2,000 in 4 years. Okay. All right. Well, let's see. 4 times 5 is 20. So let me just rewrite this a little bit better. And all we need to do here is, this is a number. Believe it or not, this is a number that is multiplying P. So we just need to divide by the quantity E raised to the 0.20 power. And so therefore the principal will be, let me just write it out. And time for the calculator. 2,000 divided by E raised to the power of 0.20. And I get that the initial investment, how many decimals are 2 decimal places? 1637.46. Okay. Nearest cent, that is 2 decimal places. Number 22, solve the following system. Okay. I'm going to use whatever is the easiest method to do. And right now I am going to use the elimination by addition. So I am set on eliminating y. I want to get rid of y. Let me take that back. I am set on getting rid of x because one is already positive, the other one is already negative. But I need these coefficients to be the same. One positive, one negative. So I am going to say, you know what? I'm going to multiply this by 9. I'm going to multiply this by 4. Why? 9 times 4 will be 36. 4 times negative 9 will be negative 36. I will be guaranteeing that the x's go away. So we got, okay, let's see. I'm going to try to do this now. Now that I know what's going on, let's go ahead and let's get going. That will be 36 x's minus 45 y's is equal to 27. Most people forget to multiply the number on the other side of the equal sign. Negative 36x negative 8y is equal to negative 80. Okay. Notice that when we add the two equations, now the x's go away. And we get negative 53 times y is equal to negative 53. Divided by negative 53, we get that the value of y is equal to 1. So now we can go ahead and use, doesn't matter which equation we use now, to find the value of x. 4x minus 5 times 1 is equal to 3. 4x minus 5 is equal to 3. Let's add 5. We get 4x is equal to 8. Dividing by 4, we get x is equal to 2. So the answer is 2, 1. Okay. Moving on to the next example. Oops. Two systems of equations are given below. Okay. Oh, I think right now I want to go ahead and use the elimination method. I see a positive y, I see a negative y, cancel that out. We get 8x is equal to negative 16. X is equal to negative 2. Okay, so the system does have a unique solution. Okay, and 4 times negative 2 plus y is equal to negative 8. Negative 8 plus y is equal to negative 8. I'm adding 8. Adding 8. Y is equal to 0, and that is perfectly fine. That is perfectly fine. For system B, I think I want to use substitution. Look at the fact that there is one equation that says y equals. So here we go. 4x minus 4x plus 4 is equal to negative 4. 4x minus 4x minus 4 is equal to negative 4. The x's go away, and we get negative 4 is equal to negative 4. This is true. Therefore, the system has an infinite number of solutions. And what are those solutions? Y equals 4x plus 4. Remember that that means that there's one line, and then on top of that line, oops, I didn't do a good job there. There is one line, and then the other line is just on top of it. Okay, that's all that is. And therefore, the solutions are just every point that makes up that line. All right, let's go ahead and move on here. Number 24. They want us to solve the system. Okay. Once again, it looks like, oh, wait, I think they want us to follow the order here. So there were 25 questions. Where is number 25? Oh, right here. Oh, no, we're not doing 25. We're not doing 25. Okay, we're not doing 25. Okay, that will not be on the test. All right, so it seems like it's time for me to show you how I would do this using matrices. Here I go. I need a 1 in the very first place. Swapping rows won't do us any good. But what I can do is I can multiply row 1 by 1 over 5 by 1 over 5, and that will get us the one that we need. Notice that negative 30 times 1 over 5 will be negative 6, and 25 times 1 over 5 will be 5. The instructions said that you're only changing R1. The instruction says that we're only changing row 2. No wonder why row 1 stayed the same. So it seems like we need a 0 here. Here we need that a 0. So we need the help of row 1. What do we need to do? If this was a 6, then 6 plus negative 6 will be 0. So everything in row 1 needs to be multiplied by 6 so that when they're added, it will lead to this result. Okay, let's look at the next sentence. Only row 2 is changing. No wonder why row 1 stayed the same. But what happens is that after this number becomes a 0, then this number needs to become a 1. And row 2 can do that by itself by multiplying by 1/2. Okay, so this number needs to be a 1. 2 times 1/2 will be 1/2. Negative 4 times 1/2 will be negative 2. And then this number needs to be 0. But row 1 cannot do that. So to get zeros, rows need help from other rows to get that 0. It cannot do it on its own. So it needs the help of row 2. What should we multiply 1 by so that when it's added to negative 6 will be 0? That will be 6. Okay, that will be 6. Okay, so that becomes okay. So notice that only row 1 is changing, so this number right here remains the same as negative 2. Okay, so what's this number here? 6 times negative 2 is negative 12. Negative 12 plus 5, that will be negative 7. So therefore, the answer for x is negative 7. Excuse me. The answer for y is negative 2. Again, do not do this problem on the review. We're not going over that. These are the 24 problems that you need to do for the review, and hopefully this will help you, okay? Use it, use it, use it. Till next time, I'll see you in class. Bye-bye.